Welcome back to Introduction to Machine Learning. I'm Ludwig Brotmann, and in this video we will try to answer the question why we can't just use the L2 and L1 loss that we know from regression on probabilities for classification as well. And it turns out that actually, to some degree, we can use those losses for classification as well. We will first look at the L2 loss on probabilities, which is also called Brier score. See the loss function, the risk minimizer, and the optimal constant model of this, and then treat the L1 loss on probabilities and speak about calibration. The Brier score is just a name for the L2 loss on probabilities. So let's say we have probabilities from the interval between 0 and 1, and the target is encoded as 0 and 1. So the L2 loss on probabilities is just the difference between the predicted probability and the target squared, right? That's really just the L2 loss. This thing, if we look at it here on the left-hand side, is convex in pi. It's a convex function, well, it's just a quadratic function. But if we look at it as a function in f, so in the model, then it's not longer convex. So that depends, of course, on how we define f, but usually we say f is, for example, the log odds. And then we have that sigmoid function, and then with that sigmoid function here on the right-hand side, this loss is not longer convex, right? Here it would be okay, but if I try to connect these two lines, it's below the loss function, so it's not convex anymore. An exception would be if, as the model for pi, we just use a linear model, the so-called linear probability model, which is quite uncommon in machine learning and statistics. Guess why? So this thing here is of course not bounded to 0, 1. So this can be anything in R, which is very much not desirable for probabilities. There is literature where people use this and they don't care so much, but it's really quite uncommon to use that. Okay, that was the Brier score loss function, and now we can look at the risk minimizer. And it turns out that as for the Bernoulli loss, the risk minimizer is the true probability, which means that also the Brier score is a proper scoring rule, as it attains the true probability of the outcome. We can also define the Brier score for a multi-class classification, so more than just two classes. And then also the risk minimizer is just the true probability that the target has exactly that class, well, given some features x equals x tilde. Let's prove that only for the binary case for this video here. So we need to minimize the risk, which is the expected loss. And again, with the law of total expectation, we can write this as expectation with respect to x of this inner part here. And as we're looking for the pointwise optimum, we can just optimize the inner part. So we can ignore this part. Now we can plug in the Brier score and look at the argument here. So first we need the Brier score for 1, which is c minus 1, right? Because, well, it's pi minus y, pi is c in that case, and if y is 1, then we have c minus 1. And on in the second summand of the sum here, we have the Brier score. If we plug in 0 for y, that's then just c. So c squared. And then we try to minimize this thing here. What we do now is that we can multiply out these terms, so this binomial formula and this part here, and we get this term, the second term, and that one here. You can check this with pen and paper. It should be really straightforward. But if we now do a small trick and we just insert 0 by adding and subtracting the square of eta here, then let's clean this first. we can ignore those parts here because we are looking at the argmin with respect to c, but this minus eta squared plus eta does not really change the argmin. Of course, it changes the value of the minimum, but not the point where the argmin is, the point where the min is, so the argmin. And then the first part here is just again a binomial formula. So we end up with that part here, c minus eta, then squared, and that is obviously minimized for c is eta because it's positive and 0, or non-negative, and it's 0 if c is eta, right? So with this we proved that the risk minimizer of the Brier score is the true probability, which means the Brier score is also a proper scoring rule. Okay, now we can look at the optimal constant model of the Brier score as in the L1-Loss chapter with respect to the empirical risk. So we are looking for the argmin of the empirical risk, which is this formula that is again just the fraction of class 1 observations in the observed data. You can either try to do this on your own, or you can just say it follows directly from the two proof for regression where we said that, well, the estimand is the expected value, and the best estimator for this is, of course, the arithmetic mean. So yeah, that's the optimal constant probability model. We can derive the same thing for the multi-class Brier score. It's just the fraction of the class K observations in that term here. So we have an indicator function of yi equals k. So that's 1 if the true class is k and 0 otherwise, and we just sum those up and divide by n. Okay, in the proper scoring rule chapter, we already spoke about the fact that the Brier score is a proper scoring rule. It's even strictly proper, which means it can be used for calibration. And calibration is now very, very much related to proper scoring rules. This is the definition of a calibrated predictor. So we have a predictor pi, and we say it's calibrated if the probability that the true target is y, given that we predict p with our predictor, that this probability is equal to p for all p from 0 and 1. So this means if we predict probability p, then in p times 100% of the cases we observe y is 1, and in the other cases we observe y is 0. So we are neither overconfident or underconfident, so it doesn't happen that we predict 99% all the times, but that's wrong. But we are perfectly calibrated. And these proper scoring rules, of course, enforce this calibration here. And so, thus also the Brier score. So this means that if we use the risk minimizer for the Brier score, which is the true probability, then we directly see that the optimal predictor satisfies this definition of a calibrated predictor. Because, of course, if we predict p, then we predict p because it's the true probability, and yeah, then we're finished here, because then we have on both hand sides here the true probability, p or eta. Okay, as last part here, we can look at the L1-Loss and ask ourselves if we can use that L1-Loss on probabilities as we did for the L2-Loss. And, well, first, the definition, it's again the absolute value of the difference of between the true probability, or between the predicted probability and the true target. So the absolute residual, if you want to call it that. And we already showed in the proper scoring rules chapter that L1-Loss is not a proper scoring rule. So we should not really expect any good calibration characteristics of this L1-Loss on probabilities. And we have the same convexity problem as we had with the Brier score. So it is convex in pi, right? But as a composite function, if we, for example, use the logouts again, then with the sigmoid function, it is not convex loss function in the score, because this thing here is below the loss function. So the L1-Loss on probabilities is neither a proper scoring rule, and we also have the convexity problem. So, well, perhaps we can technically use it, but I would definitely recommend not to use this one.